The root zone of a crop in a certain soil has a field capacity of 40% and permanent wilting point of 10%. We have to determine the depth of moisture in the root zone per meter at FC and PWP and the available depth of water if the root zone depth is 1.3 meter. The dry unit weight of soil is given as 15 kilonewton per meter cube. So depth of moisture corresponding to Fc, that is the depth of moisture at field capacity, we have the equation as Fc into gamma S into D by gamma W. And here the depth of moisture in the root zone per meter at Fc and PWP is to be found out. So we are going to take this D equal to 1, that is per meter means we are going to divide this whole thing by D or simply take D equal to 1. Therefore we are taking the value of Fc is given as 0.4 and D equal to 1, then 15 is the gamma S value is given as 15 kilonewton per meter cube and gamma W is 9.81 kilonewton per meter cube. Therefore solving that we will be getting the value as 0.61 meter per meter depth of a root zone. So that is asked in the question. Now second part, the available depth of water we have to find out if the root zone depth is given as 1.3 meter. For that simply substitute. Okay, one more thing, we have to find out the depth of moisture at permanent wilting point also. So for that simply substitute the value of permanent wilting point percentage as 10%. We have to substitute it as 0.1 into we are taking D equal to 1 as we are going to find out the value per meter of root zone into 15 by 9.81. So the value is 0.15 meter per meter depth. And for the second part, you have to find out the available depth of water. So root zone depth is 1.3, that is available moisture is available water equal to Fc minus PWP, that is equal to 40 minus 30, sorry 40 minus 10, that is equal to 30%. For therefore depth of available water, this is depth corresponding to available water TW, that is equal to Fc minus PWP, that is what we have done here, that is 30% into gamma S is 15, D is given as 1.3 in the question and gamma W is 9.81. Therefore 30% means corresponding to that we are taking it as 0.3 into 15, that is a dry unit weight of soil into root zone depth divided by gamma W. So we will be getting the value of 0.6 meters. Okay, here we have to find the capacity of a soil for the following data. Here root zone depth is given as 2 meter, existing water content is 5%, then dry density of soil is given as 1.5 grams per centimeter cube, water applied to the soil is 500 meter cube, water loss due to evaporation etc., that is the losses is given as 10%, and area of the plot is given as 1000 square meters. So here capacity means, what they mean here is a field capacity, that is we have to find out Fc. So first of all, here water applied to the soil is given, that is 500 meter cube, and losses are given, that is 10%. That means 10% of this 500 is accommodates the losses. Therefore water used in the soil is, or water available in the soil is 500 into, that is 90% is available, 10% is the losses. Therefore 500 into 90 by 100, that is equal to 450 meter cube is the water available for plants, and this 450 meter cube is converted into gram, that is 450 meter cube is equal to 450 into 1000 kilogram, that is again multiplied by 1000 to get the value in grams, that is 450 into 10 raised to 6 gram, that is 450 into 10 raised to 6. Therefore total dry weight of the soil. Now here we have to find out the total dry weight of the soil. For that, dry density of the soil is given, that is 1.5 gram per centimeter cube, and total dry weight, therefore dry density is given, so you can find out the dry weight for a soil portion of 1000 square meter area and 2 meter depth. That means we have a area of 1000 meter square and the depth is 2, that is this much height is 2 meter, that is the root zone depth. So we can find out the weight of this much volume of soil, that is equal to 1000, that is area, into 2, that is volume multiplied by 1.5 into 10 raised to 6 gram. Here this 10 raised to 6 is added to convert the meter cube to centimeter cube, that is here, see, 1000 and 2 are in meters, that is 1000 meter square is equal to 1000 into 10 raised to 4 centimeter square, and again 2 meter is there, therefore 2 meter is 2 into 10 raised to 2 centimeter. Therefore dry weight is calculated as dry weight is equal to 1000 into 1000 meter square, that is 1000 into 10 raised to 4 centimeter square, into this 2 meter, that is 2 into 10 raised to 2 centimeter, into 1.5 gram per centimeter cube. As this unit is given in centimeter cube, we have to convert everything to centimeter. Therefore here what we obtain is this much gram. Now from the total dry weight of soil and total water added, we can find out the percentage of water added, that is as a percentage of weight of soil, that is this 450, that is water used is 450 into 10 raised to 6 divided by total dry weight, that is equal to 1000 into 2 into 1.5 into 10 raised to 6 into 100, that is to convert it to percentage. Therefore 450 into 10 raised to 6 divided by 1000 into 2 into 1.5 into 10 raised to 6, that will be obtained as 15%. Now this is the water content after adding 500 meter cube and then after removing the 10% of water as losses, that is after adding 450 into 10 raised to 6 gram of water into the soil volume, the water content of the soil will be obtained as 15%. Now new water content is, there is existing water content of 5%, therefore new water content is 5 plus 15, that is equal to 20%. Therefore field capacity will be obtained as 20%. So field capacity is the capacity of soil to hold water, that is 10% of water will be lost as losses, and after that we will be finding out the percentage of water added with respect to the dry weight of soil, that is we will be finding out the new water content added due to the addition of water. So that water content added is 15%, and again there is existing water content of 5% in the soil, that is given in the question. Therefore total new water content is 5 plus 15, that is equal to 20%, and hence field capacity will be obtained as 20%. Okay, let us move on to the next question. Here a loam soil, that is a type of soil, loam soil has a field capacity of 22% and wilting coefficient or wilting point of 10%. Now the dry unit weight of soil is 1.5 gram per centimeter cube and roots on depth is 70. We have to find out the storage capacity of the soil, and then irrigation water is applied when moisture content falls to 14%. If the water application efficiency is 75%, we have to determine the water depth required to be applied in the field. So first let us draw that pictorial representation. So this is saturation, this is field capacity, and this is wilting point. So field capacity is given as 22% and wilting point is given as 10%. Now let us see, we have learned a term known as temporary wilting point. Let us say irrigation water is applied when moisture content is decreased to this point, temporary wilting point. So as we know, when we apply irrigation, the field will be reached, or the water content in the field reaches up to field capacity. From there, when the plants utilizes the water content decreases and goes on decreasing, and first it reaches temporary wilting point and then it reaches wilting point. So at this temporary wilting point we again provide water, that is this 14%, that is irrigation water is applied when moisture content falls to 14%. Therefore let us say temporary wilting point is 14%. Now this much data is given. First, we have to find out the storage capacity. Storage capacity is equal to the available moisture. You have to keep that in mind. Storage capacity equal to available moisture. So, available moisture, we know available moisture is equal to Fc minus wilting point. That is, here it is 22% minus 10%. That's equal to 12%. Now here we have to find out not simply the percentage, we have to find out the depth corresponding to this 12% of water, and for that we have learned an equation Fc, Fc, that is equal to depth corresponding to field capacity is equal to field capacity, that is in percentage, into gamma s into d, that is depth of root zone divided by gamma w. Similarly, depth corresponding to wilting point can be found out as wilting point into, that is in percentage, into gamma s into d by gamma w. Now let us say available moisture, that is depth corresponding to available moisture, is equal to y Fc minus y Wp. That's equal to, by subtracting YWP from YFG, that is equal to, from these are the equations. So from that we will get this gamma S, D and gamma W are common terms, therefore let us take it outside. Gamma S into D divided by gamma W multiplied by Fc minus Wp. So by doing this you will be getting the depth corresponding to available moisture, and that is what it is done here. Here let us see, available moisture is equal to, we said it as field capacity minus wilting point, and to find out the depth corresponding to that we used this equation, that is what we just derived, this equation. So gamma S, that is the gamma itself, gamma S into D by gamma W into Fc minus wilting point, that is gamma D. So gamma S is given as, here it is 1.5 gram per centimeter cube multiplied by root zone depth is 70 centimeter, convert that to meters, that is 0.7, divided by 1, that is gamma W. Gamma W is a unit weight of water, that is 1 gram per centimeter cube. So that multiplied by field capacity minus wilting point, that is field capacity is 22%, so that is 0.22 minus 0.1. So solving that you will get the value of depth corresponding to available moisture as 0.126 meters, that's equal to 12.6 centimeter. So that is a depth of water corresponding to available moisture, that is Fc minus Wp. Now depth corresponding to or depth of irrigation water, that is, we said the subsequent irrigation is provided when water content is decreased to this point, that is a temporary wilting point, which is taken as 14%. So we have to, next we have to find out the water or depth of water corresponding to that value, that is the irrigation or water applied in subsequent irrigation, that is or this gap is the water available per irrigation, so that the water content is increased from temporary wilting point to field capacity, and this difference, field capacity minus temporary wilting point, is equal to readily available moisture. So next we have to find out the depth corresponding to readily available moisture, that is, simply substitute the value of temporary wilting point here, that is the same equation, gamma into D divided by gamma W into field capacity minus optimum moisture content, that is the moisture content at which we provide next irrigation, that is given as 14% in this question. Here for 1.5, that is a unit weight of soil into 0.7, that is root zone depth 1, unit weight of water into field capacity minus optimum moisture content is 0.14 meters. So from that you will get the value of depth corresponding to irrigation water, that is the irrigation water that we actually provide in each irrigation. So total 8.4 centimeter depth of water is provided for each irrigation. Now from this there is a water application efficiency value is given as 75%. Therefore, to determine the depth of water required to be applied in the field, we divide the depth of irrigation water divided by application efficiency 0.75, that is 8.4 divided by 0.75, that is 11.2 centimeter. So this is the final answer, that is the amount of water that has to be applied in the field so that after losses this much, that is 8.4 centimeter water is available in the field. So the final answer is 11.2, that is the field irrigation requirement. Okay, this is another question to find out the frequency of irrigation. Here the question is, after how many days will you supply water in order to ensure the efficient irrigation of a given field? And the field capacity of soil is given as 27, permanent wilting point 14%, density of soil 1.5 gram per centimeter cube, effective depth of root zone 75 centimeter, daily consumptive use for given crop, that is 11 mm, that is a daily usage of water. So here we can find out the available moisture, that is equal to available moisture equal to Fc minus Pwp, that is equal to 27 minus 14%, that is equal to 13%. That is found out here. Available moisture is field capacity minus permanent wilting point, that is 13%. Now here the readily available moisture content value is not given, so we are going to assume the readily available moisture to be 80% of available moisture, that is 13 into 0.8, that is 10.4%. So if we go draw the figure, this is saturation, this is Fc, this is Pwp, and this is the optimum moisture content, or sometimes known as temporary wilting point. So saturation is 100%, Fc is here 27%, then permanent wilting point is given as 14%. So this available moisture is Fc minus Pwp, that is found out as 13%. So to find out the optimum moisture content, we have to subtract this, that is optimum moisture is equal to Fc minus temporary wilting point, that is this level, that is equal to 27 minus 14, sorry 27 minus 10.4%, that is Fc minus temporary wilting point of readily available moisture. So that's equal to 27 minus 10.4, that is 16.6%. So that is what we have found out here. So we have got this level. So now we know that irrigation is to be applied when moisture is raised or moisture is decreased from 27% to 16.6. Hence by irrigation we will be raising the water level from this is 16.6 to field capacity, that is 27%. So now we have to find out the depth of water corresponding to this 27 minus 16.6, that is equal to 10.4%. That is we have to find out the depth of water corresponding to the readily available moisture content. So for that we know the equation, that is gamma into d, that is d is the root zone depth, gamma is the unit weight of water, and gamma w is the gamma is the unit weight of dry soil and gamma w is the unit weight of water into field capacity minus optimum water content, that is substituting here, gamma is 1.5 gram per centimeter cube, d is the root zone depth given as 75 centimeter, that is converted into meters 0.75, 1 is the unit weight of water into 0.27, that is field capacity minus optimum moisture content level, that is 16.6 that we found out here. So 0.27 minus 0.166, that is equal to 0.104. So the depth of water corresponding to available corresponding to the irrigation water supplied is equal to 0.117 meter, that is equal to 11.7 centimeter. Now depth of water available for evapotranspiration due to irrigation is 11.7 centimeter, and daily consumptive use of water equal to 1.1. That is the daily usage of water. In one day, 1.1 centimeter of depletion takes place. Therefore, watering frequency, that is depth available due to irrigation is 11.7 and 1.1 will be depleted per day. Therefore, watering frequency is equal to 11.7. That is the total depth available by usage per day. That's equal to approximately equal to 10 days. So water should be applied after every 10 days. So 10 is the frequency of irrigation. Okay, this is another sample question for finding out the frequency of irrigation, and this question is almost same as the previous question. So you can use the previous method used in previous question to solve this problem. And here from available moisture, that is from field capacity and permanent melting point, first we find out available moisture, then we found out readily available moisture as 0.75 percentage. That is you can take it either as 0.75 percentage, so that is better. In some textbook it is taken as 80 percentage or 0.8. Therefore it is preferable to take it as 0.75 of 15%. So readily available moisture is 11.25. Now optimum moisture is Fc minus readily available moisture, that is 16.75. That means that moisture will be filled by irrigation between 16.75 and 28. That is, if we draw the figure, this 28 is field capacity. This is permanent wilting point, that is equal to 13%, and optimum moisture level, that is 16.75. So we will be increasing the moisture content from 16.75 to 28. So now we have to find out the corresponding depth of water, that is gamma S into d by gamma W into Fc minus optimum moisture content. That is Fc is 0.28 and optimum moisture content is 0.1675, that is 0.16 approximately. 1.3 is the unit weight of soil, 1 is the unit weight of water, 0.7 is the root zone depth. So you will be getting the depth of water as 10.92. So frequency of irrigation is 10.92 divided by consumptive use, it is 1.2, that is equal to 9.1 days. That is approximately taken as 9 days. So while rounding of the value, you have to round it to the, not to the next number, to the previous number. That is, if it is 9.1, round it off to 9. If it is 10.4, round it off to 10 only, not 11. So thank you.